Thanks for watching, guys. This is review for test 2. Please watch this video and take a look at the PowerPoint slides and book before you do the test. The test is going to cover chapters 5, 11, and 10. So this is our review, and we are going to cover chapters 5, 10, and 11. Right? The things that you will need to know are drag. Right? So, what is the equation for drag, and how do we use it to calculate work? Right? So, what is the drag force? A really useful equation is D equals 1/2 times C, the coefficient of drag, times rho, times A, the cross-sectional area, times V squared. Okay? So you should understand what this equation means. So C is our coefficient of drag. This is something that can be determined experimentally. You may have to determine it for a given problem, or you might be given it. So if you recall our work with the blue whales, we were actually able to make an estimate of what the coefficient of drag was. So A is the cross-sectional area, V is our velocity, and rho is the density of the fluid that you're moving through. So whatever the liquid is, if it's a gas, or it is if it's a gas or a liquid like water, then you could calculate its density. And density is equal to mass divided by volume. So in the case of a blue whale, let's draw our blue whale here. Okay? The cross-sectional area of our blue whale would be like this. So we could come up with an estimate for the area of our blue whale, and we could estimate what this was. Okay? For a blue whale, we could roughly approximate it as a circle, and we did that in class. Next, you want to understand how work is done. So work will give us energy, and work could be in the form of some force. So it could be drag or some other force. So it'd be force times distance. We looked at how the blue whale stopped over time, so D times X. So if the drag were constant and it traveled for this far, this would give us joules. Now we might want to look at power. Okay, so power is energy divided by time. So delta E over delta T. Okay, so this would be how much work are we doing per unit time. Okay, so if we wanted to know our power, then we need to know how much energy is being used per second. Okay, so that's definitely something to think about. Another thing we might want to look at is how much. Let's see. So how much work are you doing due to the force of friction? Okay, so here's my crate here. Okay, and my crate is being dragged along on some surface, and there's some amount of friction here, and so I would need to apply a force in order to keep this thing moving. Okay, so as I apply a force this way, okay, then the force of friction is going to be opposing me. So this is my frictional force. It's going to be going that way. And if I want to keep this moving at a constant velocity, I've got to keep supplying energy. So I could look at, I could say, well, how much energy am I going to have to do in order to keep this moving at a constant velocity? Then that would be the force of friction times the distance would give me work. Okay? Then you might say, well, how long did it take me to travel this far? So if I travel at this velocity, okay, I can find a distance here. I can find out how much time that took, and then I could say, what's the power? Right? What's my metabolic power that I'm expending to do this? You're also going to need to understand what the difference is between kinetic friction and static friction. So if there's a crate here, and you are pushing on the crate, okay, so here's my crate, and it's not moving, and if you are pushing back on the crate by, say, an amount F, what is going to be the force that the crate pushes back on you? Okay, so if it doesn't move, let's say I push on the crate by 30 newtons, then the crate is going to push back on me by an additional 30 newtons. If the crate starts to slip, okay, then the coefficient of friction is going to change, and that will be different. Okay, so then you'll need to know the coefficient of kinetic friction, which is usually always less than the coefficient of static friction. So know when to use each of those, what things you'll need to know in terms of friction. Okay, so let's take a look here. Then you need to know how to also calculate the weight. Right? So if I wanted to calculate my weight, right, weight is not the same as mass. Right? So if I want to calculate weight, I would take my mass times the acceleration due to gravity. And G on Earth is 9.81 meters per second squared, or 9.8 meters per second squared. But this could be different on different planets. Or, so how would you calculate this, say, on Pluto or Mars? What would happen to your weight if an elevator was moving up or down? Would that affect your weight? What would that reading on your scale say if you were in an elevator? Okay. Then, of course, we talked about potential energy. Okay, so there is a conversion that happens between potential and kinetic energy. Okay, so let's say I throw a particle. Okay, so my particle starts off of here, and let's say it starts up here, and it has some potential energy. This is U equals mg times h. If I let that particle go, then at different points, that energy is going to be converted into kinetic energy, 1/2 mv squared. So depending on what the ultimate height is here, okay, so there's my height, okay, then I can figure out what is its velocity at certain points depending on how far it's how far my particle has fallen. Okay, so understand how to convert between kinetic and potential, and that the total energy does not change. So if you don't have drag or anything like that, the total energy is going to stay the same. Now let's talk about chapter 11. Okay, so we can talk about our power, our metabolic power. Most living organisms are 25% efficient. Okay, so let's say something uses a certain amount of metabolic energy. Okay, then you might say, well, um, um, yeah. So if I know the metabolic energy rate or the power, then I could say, well, how much? Let's say if my toaster dissipates, I don't know, 80 watts. Okay, so let's say, yeah, my toaster dissipates 80 watts, and me walking generates. It requires 380 watts. How much? How many toasters would I need to replace to equal that same amount of energy? So let's say when I'm walking, okay, or running, okay, so here's me running, and I guess I have my hands up here. It takes me 380 watts to do that. And let's say my toaster is going to generate 130 watts. Ryan, and I just totally made that up. I have no idea if that's real or not. How many toasters would it take to equal the same amount of power being dissipated by me? Well, it's about 3. If that's supposed to be 130 watts. Let's say this is 130 watts. There it is. How many toasters would it take? About 3. We'd be at 390. It's about that's about a human. Okay. So also understand what the difference is between chemical potential and kinetic energy. So for example, if I push a rock up a hill, okay, how does the energy work? So I convert chemical energy into kinetic energy, pushing that up the hill. Then I store it there as potential. Then sometime later I could roll that rock down the hill. Okay. So I change kinetic into potential energy, and then I can convert it into kinetic energy. So that brings us to the end of our review for now. Maybe I'll decide there's more later. Thanks for watching, and please take a look at this.
Thank you, like and subscribe down below.